Alright, so we're doing an introduction to limits. Limits are the first concept of calculus that you learn, and it is pretty much the fundamental to all of integrals, derivatives, continuity. So if you really understand limits, then you're going to be good to go. Alright, so we usually write the limit as this statement right here, highlighted in yellow. The limit as x goes to a of f of x equals L. And a is the value that x approaches, so it is an x value. And L is the value, y value that it approaches. So a is the x value and y is the L value. If you look at the graph to the right, you'll see f of x, a function f of x, and at the point A, both sides of the graph, follow the blue, are approaching the same number, and both sides are approaching that L value, f of x, at the value, y value of L, okay? So that's what a limit is. The limit technically is not what the value is, but what both sides are approaching. So if both sides are approaching a certain number that's close to L, then you would say that the limit equals L. Okay, if you look at the first graph of x equals x plus 3, you'll see a linear function with a y-intercept of 3 and a slope of 1. The table of the values of the function is shown below as well as the graph. So we drew a table of values here that you would see typically in the calculator with increments of 0.01, 2.97, 2.98, 2.993, 3.01, 3.02, 3.03. And if you look at the values from both sides as you go down towards 3, this side gets closer to the value of 6, right? And if you approach it from the left-hand side also gets closer to 6. If you look at the graph at around the y value of 3, so let's just draw a straight yellow line at 3 and see what we're looking at. So if I'm looking at the y value of 3, from the left-hand side, my values are getting closer to 6. And from the right-hand side, my y values are getting closer to 6, the y value of 6. So, to answer the question below, notice that as x values approach 3 for the function f of x, the y values approach 6, and they eventually reach 6. Okay, so from the previous example, the way that you would write the limit statement is the limit as x goes to 3 of x plus 3 equals 6. Now if we look at the function x squared minus 9 over x minus 3, you would look at the graph, which is this first graph right here, and you would see that it looks like it goes straight through from beginning to end. But if you look at it closer and you look at the table, you'll see a hole at 3, and that's why we have an error. Both sides, however, go closer and closer to 6, the same way that the previous example did. So both sides went closer to 6, the only problem was that there's a hole at 3, and that's why there's an error there. So if you look at the graph, there's actually technically a hole at 3, and so when we look at where it intersects 3 and we do the left, approaching from the left and approaching from the right, both sides are still going towards 6. It just doesn't exist at 6. So just as before, we can say that the limit of x squared minus 9 over x minus 3 equals 6, just like the previous example is. So the limit of a function doesn't necessarily need to be a defined value of the function. It just means that both sides approach it. And if you look at the equation x squared minus 9, you can factor it to x minus 3x plus 3 all over x minus 3, and you'll see that there's a hole at x minus 3. So it's really the same graph as the previous example, only with a hole at 3. Okay? Okay, So let's do an example of finding limits from a graph. So as x goes to -5, I'm looking at the line -5. So I'm going to draw a line at -5. And from the left-hand side and from the right-hand side, I am going towards a y value of 4. So my limit as x goes to -5 of f of x equals 4. Part B, I'm looking at 2. So I go to 2 and I'm looking along that yellow line at 2. From the left-hand side, I'm going towards 3. From the right-hand side, I'm also going towards a y value of 3. Since both sides are going to 3, my limit as x goes to 2 is 3. For part C, my left-hand side is going towards 0 and my right-hand side is going towards 8. So since they go to two different numbers, the limit does not exist. And for part D, looking at number 4, the left-hand side goes to 0 and the right-hand side goes to 0. So my limit as x goes to 4 of f of x equals 0. Alright, so you've been hearing me talk about from the left side and from the right side. They have limit statements that also denote from the left side and from the right side. So if you look at these two limit statements, there's a minus sign right next to the A, and there's a plus sign right next to that bottom A. So what that means is the minus sign means the left-hand limit. So that means coming from the left side, what does the number approach? And the plus sign means the right-hand limit. That means coming from the right side, what does the right limit approach? So if we look at example 2 on our thing, it says find the limit as x goes to 0 of absolute value of x over x. There's two sides to it. There's coming from the left side and coming from the right side. So if we look at 0 on the graph right here, on this graph, or right here on this graph. As x approaches 0 from the left, the limit appears to be -1. So if you look, 0 from the left, it appears to be -1. Also, 0 from the left of this graph means coming from the left-hand side. It's weird because it's pointing right, but what it means is coming from the left-hand side, it's going towards a certain number, okay? So it's pointing right, but it's coming from the left. It's coming from the negative side. So don't think of it as pointing right. Think of it as the negative side. So as x approaches 0 from the left, the limit appears to be -1. To write that in limit notation, you would want to say limit as x goes to 0 with a minus sign after of absolute value of x over x equals -1. If you look at the same graph, but you come from the right-hand side, so the right-hand limit means moving left, but it's coming from the right-hand side, so on the positive side of 0, and on the positive side of 0 here, we're approaching 1. So we would want to say limit as x goes to 0 plus of absolute value of x over x equals +1. Since both sides approach different numbers, the limit does not exist because, look at this limit statement. In order for the limit to exist, the left-hand limit, the limit from the left, and the limit from the right have to both equal in order for this to exist. So left has to equal right in order for the whole limit to exist. So does this limit exist? No. Alright, let's do this example together. The graph of the function g is shown. Use it to state the values if they exist of the following. So the limit as x goes to 2 from the left, from the right, and the limit as x goes to 2 as a whole. So I'm going to draw a little line at 2 just to see what I'm looking at. And then the 2 from the left is going towards a y value of looks like 3 to me. 2 from the right, let's go 2 from the right, is going towards a y value of 1 for me. The limit as x goes to 2 as a whole, if the 3 and the 1 aren't the same number, then the limit as x goes to 2 does not exist. Okay. For D, draw a line at 5. The limit as x goes to 5 from the left is 2. The limit as x goes to 5 from the right is also 2. Since both sides go to 2, then the limit as x goes to 5 is also 2. Now you might be asking yourself, what about that rando point that's right there below it? Well, that is what the function g of 5 is defined as. So if you plugged in 5 into the equation, you would get a y value of 1. That doesn't mean what the limit is. So the limit doesn't actually care what the rando point is on the outside. The limit only cares about what the sides of the graphs are approaching. And if the sides of the graph are both approaching the same number, then that number is what the limit is. Okay, unbounded infinite limits. Since the limit as x goes to a of f of x does not exist unless it goes towards a specific number, then technically the limit does not exist. But if they both go to positive infinity or they both go to negative infinity, then it still means that the limit does not exist, but it fails to exist in a special way. So if they both go to positive infinity or they both go to negative infinity, then you would want to say positive infinity or negative infinity. Let's do an example of both types. Take this graph for example. The limit as x goes to 3 of x plus 2 over x minus 3. Now, if you were to follow the left-hand limit of this graph, it goes towards negative infinity. If you look at the table, it also goes towards negative infinity. So the left-hand limit would be written limit as x goes to 3 from the left of x plus 2 over x minus 3 equals negative infinity. From the right-hand side, sorry, I didn't pause it, but from the right-hand side, it goes up. And from the chart, it also goes to positive infinity. So you would write the limit as x goes to 3 from the right of x plus 2 over x minus 3 equals positive infinity. Does the limit as x goes to 3 of x plus 2 over x minus 3 exist? Well, since they go to opposite infinities, we would say no. All right, but the next example, hold on one second, shows both sides, the left-hand limit going towards positive infinity and the right-hand side both going towards positive infinity. So since the limit as x goes to 0 from the left of 1 over x squared equals positive infinity, and the right-hand limit of x goes to 0 from the right of 1 over x squared equals positive infinity. Since both go to positive infinity, does the limit as x goes to 0 of 1 over x squared exist? Technically, no. But you would want to say positive infinity anyways, because that's what we do in math. We try to give an explanation of where it's going towards, and since they're both going towards positive infinity, a better explanation of the limit is to say no, but they're both going towards positive infinity, so we'll put positive infinity to give them a slight direction to it. Okay, these two examples are the last two limit examples that we're going to do. So when you look at this limit statement, limit as x goes to 0 of x minus cosine x over 1,000, when you graph the function, both sides appear to be 0. So if you follow from both sides, it seems to be going towards 0 for the y value. However, if you look at the table, the y values are actually getting closer to negative 0.01. So if you have a table or if you have an equation, then you're going to want to examine it more closely. If you don't have an equation, then you go towards your best guess, which is 0. But since we have the table and we have the graph, we know that our limit is negative 0.001 instead of 0 like it looks. Example 6, find the limit as x goes to 0 of sine of 1 over x. Now if you notice, these values here go from negative to negative, and then error, and then positive, negative, positive. Well, when you look at the graph, it's going like up and down, all like crazy like in the middle before it continues on. So we call that a wild oscillation. Now when you have a wild oscillation, then the limit does not exist because you cannot come up with one defined value for the limit because it's just going crazy in the middle. So if you ever have a wild oscillation graph, you would say the limit does not exist. So there are 3 times where the limit does not exist. Now the first time technically is when the left-hand limit does not equal the right limit. The next time a limit does not exist is if the limit approaches infinity. And the last time that a limit does not exist is if it's a wild, how do they spell it? Wild oscillation. Okay? So, do these last 3 examples. You might want to pause the video, do the last 3 examples, then check your work with me, and start on your homework. Okay, here are the answers to the last 3 problems. The limit as x goes to 3 from the left of 3 minus x over x minus 3 equals 1. If you were to graph that, you would see a graph that changes from 1 on the left-hand side of 3 to negative 1 from the right-hand side of 3. So the left-hand limit is 1. If you were to graph this equation, then you would have a graph that intersects at 1 and a slope of 3 up to 2. And this y value is 7. Then we have a point at 8. And then x squared plus 3 from 2. 2 squared plus 3 is 7, so 7 to infinity would keep increasing like that. So the limit of that function at 2 is 7. Decide if the following are sometimes, always, or never true. If the limit as x goes to 2 does not exist, then the limit as x goes to 2 from the right does not exist. That's sometimes true. What if the limit as x goes to 2 from the left does not exist? Then the limit as x goes to 2 would not exist, but the limit as x goes to 2 from the right may exist. Part B, if the limit as x goes to 2 from the right of f of x does not exist, then the limit as x goes to 2 of f of x does not exist. That is always true. Okay? If you have questions, make sure you ask them in class. You'll have a quiz, so be ready to take that, do your homework, check your answers, and I will see you soon. Bye.